Hello everyone and welcome to another JSO tutorial. In this tutorial we're gonna continue the part 3 of creating your model manually. So in part 1, which was actually one video divided in two, we created this problem, which is the generalized Rosenbrock, one of the Rosenbrock's extensions. And it's an unconstrained problem. And we saw in the last video how to implement its objective function manually here, right here, its gradient, the product of the Hessian with a vector, any vector. This is my cat. So as I was saying, we have the product of the Hessian at a point x with a vector v, and we also define the Hessian that has structure and the Hessian values. Okay, so this was in a triplet matrix format. So this is essentially a bunch of tests that we made. We have compared this manual model with a model with automatic differentiation and with a model from a jump and NLP models jump. And our model was faster, and except in a few instances where we had a very small difference. Okay, for instance, here computing the Hessian, our model takes 600 nanoseconds, and the other models takes about 3 times as much at least. Okay, so this can be seen in other videos. Today we're gonna implement a constraint problem. So I don't want to spend too much time writing a problem, of course. So what I'm gonna do is I'm gonna take the problem we used in the last video, this one, and I'm gonna add some constraints to it. Okay, so this is gonna enable me to just implement the constraints function. So I'm gonna add some nonlinear constraints here. I actually don't know if the model is gonna be able to solve it, but if the IPOpt is gonna be able to solve this, I'm just worried about adding constraints. So I'm gonna add 3 constraints. One of the constraints is gonna be x1 square. Oh, this is not the this is gonna be the sum of xi squared, because I have a lot of them, not just one. And this is gonna have to be equal to, let's say, n, because we're gonna have n by 2, because we're gonna have n values and the solution to this is 1 in everything. So if we say that xi squared is the sum of xi squared is equal to n over 2, then that solution is not going to be the solution to the constraint problem anymore. The second constraint that I'm going to add, let's just say I'm going to sum xi and write something like this. Xi has to be greater than xi plus 1 plus 0.1. Okay, so I don't know if this makes any sense for this problem. I equals to 1, 3, 5, up to n minus 1. I think that's it. Let's just add these 2 constraints here. double equal is reserved to the implementation. So the sum of all xi squared is equal to n over 2, and each xi for the odd ones is greater than xi plus 1 plus 0.1. Okay, just a small thing. And we're gonna copy all this here and everything here as well. Actually, I want these two. Yeah. So our model was extended Rosenbrock, and since I can have two structs and I won't try to overwrite the previous struct because it will break, I'm gonna call this cons extended Rosenbrock. Is an abstract NLP model, again, same thing. I have a constructor extended Rosenbrock, and what I have here is my initial point is going to be the same. My number of non-zeros in the hashing, I'm going to have to update this. But first, I'm going to consider the number of constraints here. I'm going to call M to be 1 plus half of n, which is this first constraint here, the nonlinear constraint, and these other constraints here, which are n over 2 constraints. So in the current NLP model meta, at least, I think we call this ncon. And to make sure, we're gonna find the docs. Here in the stable. So here we have the number of constraints here. Total number of general constraints. The second thing, I'm gonna close this. Don't need to see myself anymore. The second thing is that I'm gonna say that I have some linear constraints. So the linear constraints that I have are from 2 to n plus 1, and some nonlinear constraints which are just the first one. Okay, so these are the indexes of the linear and nonlinear constraint. And I think that's it. If I want, I can provide a starting point, a starting Lagrangian approximation. So let me edit this a little bit. I could say I want the starting solution to be once. For some reason. By the way, this is 2 to the m. And one thing that I'm gonna need is NNZJ. So the same thing as NNZH, the number of non-zeros in the Jacobian. Actually, to be more correct, the number of elements in the triplet vectors, okay? So for now, I'm gonna say it's 0, and some things are not gonna work. Everything here is gonna have a cons. And now I'm gonna implement the constraint vector function. So I forgot to run. And I'm gonna say NLP is con extended Rosenbrock, which by default has 10 values. So no method is less unit range. So let's see, what is this? It was inside NLP model meta. I believe because this is already a vector. So there we have it. We have 10 variables, 6 constraints, 5 of them are linear and 1 is non-linear, okay? So we already know that if I have a vector, I can call the objective value, the gradient, the Hessian, and so on. Now I'm gonna define the constraint function. So here, I'm gonna search for API. And here I have the functions that I want to implement. So I have f of x, the gradient of f at x, and the Hessian of f. Now I want to implement the c of x and the Jacobian of x. And you can look here. Okay. So first, we have to say what are the right hand side and left hand side, which is not exactly correct, but what are the lower and upper bounds for the function c of x. So for this function, for this constraint here, xi greater than xi plus 1 plus 0.1, we have a explicit lower bound for some constraint. But for the equalities, it's not very clear what do we mean by that. And we simply mean that the lower and upper bounds for the constraint have to be the same. Okay? So you can define these. I prefer to define this by throwing everything in the left hand side and having a constraint equal to 0. But you can define this as a lower and upper bound equal to n over 2. Okay? And we also have to inform that to our model. So the lower constraints is gonna be 0. And for the other constraint, which is a lower, I'm gonna write this constraint here as xi minus xi plus 1 greater than 0.1. So it's gonna be 0.1 times 1, okay, and minus 1. And the upper bounds are gonna be 0 for the same equality constraint, and infinity times 1 and minus 1. You can also use few here, okay, but just to show that the correspondence, it's bounded below by 0.1 and bounded above by infinity. That is, there are no bounds, these variables. And I'm also going to inform this in my model. Now I can implement the function cons. So I just saw it here. The function for c of x, cons. Cons exclamation mark actually is the one you want to implement because it evaluates the constraints in place. So you're going to be memory efficient here. Cons extended reason block, then abstract vector x, and then cx, another abstract vector, which is gonna be the output. I'm gonna increment and I'm gonna, so let's see, what do we need here? I need the number of variables. I need the number of constraints. Actually, well, I don't need, but, and I'm gonna write that cx1 is just the sum of cx of xi square. This can be written as dot xx. It's not needed to be written this way, but I like it. And the other constraints, which are gonna be I plus 1, are gonna be x, the ith value. So I actually want the odd ones, so 2i minus 1 minus x2i. And my lower bounds are in the lcon vector, which is inside nlp.meta. So here, when I run again, I have nlp.meta lcon. So notice that before we have forgotten to add lcon and ucon, and now that we have added it, we have an equality constraint and 5 lower types of constraints. Okay, so now it's defined. Before we had 0 of everything. We have no constraints of any of these types because all of our constraints were free constraints. There you go. Now I'm gonna check cons nlpx, and cons is not implemented. I just implemented it here. Let's see. So oh, I forgot to say, no, NLP is here. Ah, I see. Here, I returned the wrong thing. Okay, so as I said before, live coding, the joys of live coding, and they never end because I forgot to implement here. Running. Everything works except that now I need dot to be defined. Dot was used here. So linear algebra. So cons nlpx is the constraint. So my starting value is not at the circumference of radius square root of n over 2. And my values xi minus xi plus 1 are all minus 2.2. Okay, nothing new here. This is the easy one, constraints. You just write the function directly. Now for the fun part. Jac. Jac is the Jacobian, okay? And the same way that I had the hash and the hash structure and chord, which are the structure of the hashing and the coordinates of the hashing, I'm gonna have Jac and Jac structure and Jac chord. So you can see here in our API, I have the Jacobian, I need Jac structure and Jac chord, okay? There is also jprod and jtprod, which are the products of the Jacobian by a vector. I'm gonna skip this one for now because we're gonna test this with ipopt, which doesn't use, so we're not gonna implement this one today. So Jac structure, let's copy this. I actually only need the first part. Is gonna receive the vector of rows and columns, and this one I'm gonna copy. And add a few padding here. And I have to return a vector of appropriate size. So my constraints are x1 squared plus x2 squared plus x3 squared plus x4 squared. Forgot the square here. So this is the first constraint that I have. I'm considering for the example n equals 4. My other constraint is gonna be know where that came from. Xi minus x2. And I have only another constraint, x3 minus x4. So the Jacobian will be the gradient of the first constraint, 2x1, 2x2, 2x3, 2x4. Then 1, minus 1, 0, 0. 0, 0, 1, minus 1. Okay. So looks like there are n plus for each other constraint, which are n over 2, I have 2 values, so another n values. So n values here, 2 here, 2 here, and this n time, n over 2 times. So total of 2n elements in the Jacobian. So this is gonna answer to us the value of n and j. This is gonna be 2n. We don't know yet the n and z age, okay, because this is gonna change. But let's ignore that for now. So n is gonna be nlb.meta n var. Rows from 1 to n. The first n rows of my constraints are gonna be all 1, which is the first constraint. And the first columns are gonna be 1 to n, which is 1 for each one of these columns here. So 1, 2, 3, 4. Now 5, 6, 7, 8. Maybe there is an easy way to write this. I'm trying to think of a way that is not too magic. So let's write it the usual way. So I have n plus I, which is not going to be I, it's going to be I over 2. So n plus divide 2. Rows j is going to be, is it row j, I, and then, okay, skip. So it's going to be j, oh. It's going to be 1 plus this thing here. So I'm actually going to remove this. It's going to be 1 plus j. Rows n plus j plus 1 is also going to be 1 plus j. Columns n plus j is going to be the first variable, which is j. No, this is going to be I. This is going to be 1. And plus j is going to be I plus 1. So the next I is going to be 3. J is going to be 2. N plus 2 is going to be 1 plus 2 is 3. And 3, which is the third row. N plus 2 is going to be I, which is 3. And also 3. Okay, this in this case they are both 3. So not very useful. Let's go to the next one. If I had another constraint here, so it's 4th row, 5th and 6th columns. So I is equal to 5. J is 6 over 2, 3. Rows is gonna be 4, 4. Okay. And the columns are gonna be 5 and 6. So looks like it's right. Return rows and calls. nlpmodels.jackchord is gonna be very similar. I'm gonna have an abstract vector as input, and I'm gonna have a vals, which stands for the values. And again, the first n values are very simple. They are simply 2 times x. And the other values, I think I can make it work by simply saying that this is n plus 1, n plus 3, n plus 5, which is exactly this. So vals of n plus 1. I'm gonna write this way: 1 to n minus 1. Okay, froze. So 1 to n minus 1 skipping 1 is gonna be the odd ones. So n plus because I'm skipping it, and all the odd ones are equals to 1. And I'm also gonna have the same thing, but for the even ones. So they are gonna be equal to minus 1. Let's enter and let's check. I'm gonna remove all this below here. Actually, I'm gonna leave because of the future people may want to check the notebook online. And I'm gonna call Jacques. So first thing is it's not working. Possibly because I haven't updated this. Let's check. No. So the first 3 arguments lengths must match: length of I, length of j, and length of v. So they should all be equal to 20. And apparently the length of v is 5. And I forgot to return vals. And row indices ik must satisfy being less than this thing. So let's just make sure we have 10 variables and 6 constraints, and then j is 20. Now something here was a mistake. Oh, let's check. So I wrote Jack here, but I can write Jack's structure. By writing Jack, it internally calls Jack structure and Jack chord for me, so it did not work at all. So I have, I have 20 values. So the first 10, 1, 2, 3, 6, 9, 10 should be the first constraint, so 1. And then I have 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, which is not the case. So I'm making a mistake here in this part. So no, this is not J, this is I. Because I'm skipping 1 here. And this should be I as well. And almost. So 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And here I have 1 2 through 10. And then 2, 0 is not correct because I forgot to add 1 here. So 1, 2, 3, 4, 5, 6, and all the way to 10. Now it's correct. And now I can call Jacques chord. It's probably gonna be wrong. Well, no, actually, because I haven't used this logic. So it's correct, apparently. And if I call Jacques directly, it creates the Jacobian for me. So as I mentioned in other tutorials, calling jack is what you want if you are teaching using this thing. If you're teaching nonlinear optimization, you want to use jack directly because it's easier. But, and the reason of this tutorial is for the specialized user. If you are a specialized user and you want the most efficient way, you're gonna want to work with the coordinates of x, or the sparse structure. So here we have matrix jack and things. Okay, so the Jacobian is there. We are almost done. We now have to update has structure and has chord. Why? Well, see, the thing is, the has chord is a function for the unconstrained case. For the constrained case, we have more values. And important thing here is that in NLP models, we do not assume uniqueness of the values in the Jacobian, in the sparsity structure. So my current has chord and the has structure, it considers that I'm gonna have only the objective function, and then it created this structure here. Okay. Now I'm gonna have another part of the Hessian, which is the second derivative of this thing. These other ones are linear, so they're gonna be 0. But the Hessian is gonna have the Hessian of f plus the first Lagrangian multiplier, because it's the only constraint that has a second order part. And the second derivative of this is only 2 times the identity, so 2i, thankfully. And I'm gonna write this. Okay, otherwise it was gonna be a lot of work. So I only have n another values, okay, n additional values. So here I'm having the NNZH equal to 3 times n divided times, 3n over 2, and then I have another n here. Okay, this could be 5n over 2, but let's keep separate so it's obvious, or at least an indicative. And here has chord has a new argument, which is y. Why? Because. So this new argument is gonna be the Lagrangian multipliers, and after doing all this, I'm gonna create a new value. So these go all the way to 3 times n minus 1 plus 1, it's n divided by 2. So 3n over 2. So let's write j equals 3 times n over 2. N is even, so don't worry. It goes from j plus 1 to j plus n. And it's gonna be 2 times yi. All of these values. That's it. Except that now I need to inform this to my structure. So j is equal to 3 times n divided by 2. And all these values are 1 over n. So one important thing here, we do not differentiate between the structure for the Hessian of the function f and the Hessian of the Lagrangian. Because if you're going to be efficient, you're going to want to have only one memory for both of these things. If you really did them separate, you can always call has structure with a different set of vectors, row and calls. But anyway, this n last value are gonna be there. So this should be done. There is the question of what do I do with these last values? You could assume that the user set them to 0, but in my experience I prefer not to assume that. And that's it. It's run again, and then z age is now 15. It was already 15. Got to update this. So when n's age is now 25, which has 10 another values in the Hessian. The Hessian at x is the same thing, is the same function that was called before. But now I'm gonna call a new function, which is, I'm gonna call has structure first to show that the structure has changed. So it has these last 10 values now. If I call has scored at NLPX, is gonna break because I forgot the x. At NLPX is gonna have 10 zeros at the end. And if I have some Lagrangian multiplier and I call has scored, it's gonna, forgot the x, is gonna have the value of the Lagrangian multiplier, which in our case is 1, times 2 at the end. If I call has, it's there. Okay, you can see the 2 here. Okay. And you can always call matrix. And if you really want to make sure that it's there, you can see it now. Okay. So now we have a model that has implemented all main unconstrained and constrained functions, both the objective, the constraint, their derivatives and second derivatives. And with that in hand, we can call IPOpt on this problem. Here IPOpt was called. It solved the problem. Important. I forgot to set the output. And let's print the output. The solution is 0.001 almost, minus 1, 001, minus 1, 0, minus 1, and so on. So actually this square, oh yeah, n over 2 is 5. So I have 10 values, minus, it's almost minus 1. There is this small space here, which is essentially the space needed for these values. So probably these two together are gonna be 1. These two together are gonna be 1, and so on. The sum of these are gonna be 5. Actually, this squared plus this squared is gonna be 1. And well, that's it. It looks like the other 5 constraints were not active. Okay, so they are very not active. Anyway, we made it. It's being used. Okay. So that's it for our constraint model. A quick reminder that if you have implemented these methods, you have the methods for the matrix free, for the linear operators already available. So if you want the has OP, which is the operator that provides the Hessian, you're gonna have it here. You can multiply this by a vector. But if you want the Jacobian of the in operator format, it's gonna fail because it doesn't have jprod implemented. Okay, so as I said in some other tutorial, when you call hasOp and jackOp, what it does is create a linear operators which provides the prod functions internally. So hasOp is a symmetric real matrix, so this is hprod times any vector that you provide, and jackOp provides jprod and jtprod. So you have to implement jprod exclamation and jtprod exclamation. So let's say you don't want to implement jprod and jtprod because you already have the sparse structure and I want to use that without explicitly writing it. So you'll have internally jackOp, rows, calls, vals, jv, and jtv. So rows and calls are the jack structure. Vals are gonna be jack chord at x. jv is a vector that has pre-allocated the output. And then when you call jackOp, you're gonna have, you're gonna have a linear operator that works as if you had the Hessian, but you don't actually create the sparse matrix. Notice that you have created rows, calls, and vals, so it's argumentative of whether you want to do this again or not. Also, you can do jack NLP times the vector. Okay, this is going to be the same thing. This one does not create a matrix explicitly. It does a for, a loop in these values. And this one creates the sparse matrix that Julia uses. Okay? So you have both options. So that's it for our constraint model. I hope you have enjoyed it, and this is the end of our part 3 of creating your model. Thanks for watching, and I'll see you next time.